Hello, my name is Christodoulou and I'm at the head of Inorganic Nanocrystals laboratory. Since the early ages, the advancement of civilization and the way we live is governed by the materials. That's why we can see that we name the material, the age with the material. So from the Stone Age, go to Bronze and Iron Age, and of course to the age of plastics and the age of transistors and silicon that were able to advance the technology and make, for example, some cameras. And nowadays we experience the atomistic age, the age that we can shape the material the way we want and we can build a material atom by atom. By able to control the material in such a high level, we can design nanomaterials and we can give to materials new properties. And these materials, they have high surface to volume ratio, so both the surface chemistry but the synthetic chemistry allow us to have access of tuning the properties of material. So here you can see that you can tune all the magnetic, the optical properties of the material by just changing the composition of the material, or by changing some atoms of the surface. You can change all the optoelectronic properties of the material. As a result, we have colloidal and quantum dots that they have excellent optoelectronic properties that they have high degree of control. We can reach quantum yields up to 99%, very stable. We can have quantum dots with an emission invisible or near IR. But most importantly, this technology is quite cheap to produce this material compared to synthetic methods that they're much more expensive. So we have materials that they have very nice properties, they are cheap, and they're solution processable. That means that the big companies they can use some liquid form of the material in order to make devices and films. So we can see that the colloidal common dots is the choice of the big companies from Samsung, Apple, Google Research. A lot of companies and private sectors have focused their research on the colloidal common dots. We can see that colloidal common dots have already been out of the market. So we can go out and buy a Samsung QLED TV. Now also LG has some QLED technology. So we can see that the potential of these quantum dots is huge. My laboratory is focused on three aspects. The main aspect is the synthesis of nanomaterials. So we make synthesis of colloidal nanomaterials with the slant line techniques, and then we tune the surface. We have the post-fractionalization techniques in order to give different properties of the material. Then, of course, we have to characterize the material because every material has different properties and we need intense characterization, both structural and optical characterization. And the end goal is to make the optoelectronic device. Mainly, we're focused on lasers, detectors, or sources, and LEDs based on these colloidal quantum dots. In general, as a lab, we produce materials on demand for solution processable optoelectronic devices. We're trying to find the technological bottleneck and translate this problem into a material problem. For the synthesis part, we are interested in three different categories. In semiconductor colloidal quantum dots that they have an absorption in near IR, metal oxides, optoelectronic devices and catalysis, and metallic nanoparticles for catalysis. For semiconductor quantum dots, we're interested in quantum dots that they have a band gap from 8 to 900 nanometers up to 2 microns. In that perspective, we study lead chalcogenides like lead sulfide, lead selenide, and their core shell structures. And on the other hand, we're interested in indium arsenide and gallium arsenide as materials for visible and near IR emission. Moreover, we are interested in metal oxide nanocrystals, so we study iron oxide nanocrystals for biological applications. We use iron oxide nanocrystals for cancer treatment, and on the other hand, we're interested in development of N and P type oxides in order to be able to tune the optoelectronic properties of the device or to be used this material as layers in optoelectronic devices. Very recently, we're interested in the synthesis of metallic nanoparticles of different sizes and shapes, and we synthesize gold and silver or nickel nanoparticles with different sizes and shapes for tuning the optical properties, but also to use these nanoparticles for catalysis as these quantum dots are ideal due to the high surface to volume ratio. Thank you very much.